Hello, everyone, and welcome to another Understanding Deep Learning seminar. Today, Gintare Karolina Ducate is going to talk to us about progress towards understanding generalization in deep learning. Karolina is a lead research scientist at Element AI, a ServiceNow company. She is also an associate member at MILA, the Quebec AI Institute. Her research combines theoretical and empirical approaches to understanding deep learning with a focus on generalization and network compression. Before joining Element AI, she obtained her PhD in machine learning from the University of Cambridge under the supervision of Zubin Garamani. Karolina, please take it away.
Thank you. Thank you for the introduction. So today I'll be presenting joint work with a number of my colleagues listed here below. My work is centered around the question, why does deep learning work? And in this talk in particular, I'll be focusing on why does deep learning generalize? Oops, apologize. So there are a lot of exotic notions of generalization, such as, data distribution shift, future learning, and so on. In this talk, I'll be focusing on the simplest notion of generalization, which is in distribution generalization. So why focus on this simplest notion? Well, there is as yet no satisfying theory explaining why overparameterized neural networks trained by variance of stochastic gradient descent generalize from training data to test data on standard benchmarks. And of course, without a solid foundation, we have little chance of understanding and taming more complex phenomena, such as out-of-distribution generalization. This gap between practice and understanding is a growing liability, especially as we start incorporating deep learning into high-stake applications such as healthcare, self-driving cars, and so on. So in this talk, I'll describe recent progress as barriers towards explaining generalization. Let me start with the backstory. A few years back, Zhang et al. Published a now kind of much cited and well-known paper, Understanding Deep Learning Requires Rethinking Generalization, where they showed that networks trained on standard data sets could achieve both zero training error and good test error without any explicit regularization. They also observed that networks had a very large capacity. So even if you memorize the labels, you could still achieve zero training error. Now, the authors noted that this implies that naive VC, Rademacher, and stability-based bounds are vacuums. And the reaction from many experts was that what was obviously missing from the story was margin and implicit norm-based capacity control. And indeed, just a year or two before that, Neishaber et al. Published a paper where they had somewhat similar observations. And they showed that SGD's generalization error, which is the difference between training and test error, was not affected by increasing network size or lack of, again, explicit regularization. And this motivated the authors to propose what they called implicit regularization as explanation. So, people believe that a likely explanation is that despite there being no explicit regularization, stochastic gradient descent has implicit regularization, perhaps controlling the norms or maximizing the margin or whatever else that gives a good generalization. And this is in line with Bartlett's work from 20 years back, where he set out to explain why large neural networks generalized. And he showed that he derived generalization guarantees in terms of the norms of the weights of the network, showing that even infinite-sized networks could generalize for as long as the norm was small. In Bartlett's work, he looked at sigmoid networks and a particular norm, L2 norm. But for Rayleigh networks, it's not really applicable anymore. So for Rayleigh networks, you can upscale one layer, downscale the other layer, and not change the output at all. And so Neishaber et al. In 2015 followed up on this work and proved generalization guarantees that depended on what they called path norm. So they proved path norm-based Rademacher bounds, where path norm was actually custom built for Rayleigh networks, so it was scale invariant. I can think about it as, the minimum L2 norm after rebalancing the weights. So what these bounds say is that no matter what the size of the network is, for as long as you have a small norm and a large margin, you'll have a small generalization error. what people didn't really seem to appreciate at the time, or at least didn't comment much at the time, is that the margin and the norms, they're of course data dependent, they're case dependent. And so one needs an empirical evaluation to understand whether these bounds explain generalization in deep learning. And that's exactly what I set out to do a few years back. So in my 2017 uriad paper, I computed the path norms for a fully connected, relatively small neural network trained on MNIST dataset. So here on the x-axis, you see the training epochs, I believe, for iterations. On the y-axis, the path norm. The path norm is growing during training, but generalization guarantee, so this difference between test and train error, is bounded in terms of the path norm divided by the margin. So for as long as you have a margin large, it's all fine. And the margin is indeed growing during training. But notice that the path norm, the scale here is, we have log scale. So the path norm is actually growing much faster than the margin. And if you evaluate the bound, which is this green line, you can see that it quickly becomes vacuous. So we are bounding a quantity which is between 0 and 1 error, and we're getting bounds that are above 1. While the training and test errors, which are these blue and orange lines, they're decreasing the training time. So one could ask, what if we explicitly regularize for the path norm to remain small? Would we get a guarantee on generalization then? And if you explicitly regularize, you see that the path norm, so these middle plots, it does decrease. So as you increase the level of regularization, it increases even more and plateaus earlier. But unfortunately, the margin, which are these bottom plots, also decreases when you start regularizing for the path norm to be small. And when you compute the bounds, these are the top two figures here on the top right corner. You can see that the bounds will come back here. And only when you have so much regularization that your training and test errors are, pretty much useless. I believe it was binary MNIST, so 50% is guessing rate. You finally get a non-vacuous bound. And so people since actually have extended these experiments. And as we'll see later, not only the bounds are vacuous, but they also scale grown correctly as you increase the number of data or vary the parameters otherwise. So what we see is that empirically, the norms are not small enough relative to the margin to explain generalization. And if one wants to explain generalization in deep learning, showing that, margin implies generalization, small margin, for example, implies or small norm and large margin implies generalization, then one needs to actually show that stochastic gradient descent does find networks with small norm and large margin. Keep getting it backwards. So the question still remains, what structure can we connect to generalization, both theoretically and empirically? So show both of these parts, that as you defines X and X implies generalization. In other words, if not margin in the norm, what structure is sufficient for generalization? By the way, I just wanted to mention that if anybody has questions, feel free to interrupt. I'll be happy to answer them as I go. So at the time, Kaskar et al. Published a paper showing that flatter minima implied better generalization. And the idea that we had at the time was that flatness means that non-trivial perturbations of the weights have the same loss. So if you look at this toy example on the right, where I illustrate the empirical risk surface, and imagine you run stochastic gradient descent, which arrives as this red dot here, and it's a minimum, then you can perturb it quite a bit within this region without changing the empirical risk at all, or by very small amounts. And this connects to actually some older ideas by Langford and Karolina, Hochreiter, Schmidt-Huber, Hinton, and Kemp, and so on. So in theory, we can connect the flatness and these invariants to, or insensitivities to perturbations via PAC-based bounds. So let me present a general PAC-based bound. There are many versions of them. So we'll assume that the loss is bounded. The nature chooses a data distribution D. We choose a distribution P on the weights that we'll call the prior distribution. So we choose it only without knowing the training set S. Then the nature gives us an ID training set sampled from this potentially unknown data distribution. And we get to know the empirical risk surface. So for example, maybe it has 2 minima, 1 flatter minima, 1 sharper minima here. Then what PAC-Bayes bound tells us is that with high probability, any posterior classifier Q on the weights in this case will have generalization error, which is bounded in terms of the KL divergence between Q and P. So again, let's look at this example on the right. So here is our parameter space, right, and the empirical risk surface. Let's say we chose a posterior classifier Q, which lies in this flat and pretty wide flat minima region. Then the KL divergence between Q and P will be smaller than the KL divergence between Q prime and P, where Q prime is another randomized posterior classifier centered at this sharp minima region. And so the generalization bound will be smaller for Q than Q prime. Now, one could say, okay, we can increase the variance of Q prime, right? If we are doing here isotropic Gaussians, we could increase the variance of Q prime. But the issue is, of course, that the empirical error will also increase. And so since the generalization error is the difference between test and training error, while the bound will get smaller, the training error increasing will, of course, mean that the test error will be worse. And so we'll not get a useful classifier. So there is this trade-off between kind of how big of a variance we can have of our posterior classifier Q and how tight our bound can be. Any questions here? Because I will be building on PAC-Bayes bound. So, okay. So in my work, I started by studying.
Excuse me.
Yeah.
So someone asked, how do we calculate the margin and path norm per epoch?
Yeah. So here I don't care about margins and path norms anymore. And in the previous work where we evaluated some of the bounds, I just took the classifier that I had at time t, and I looked at the margin, which is just the, or I looked at at the margin, which is just the difference between the true label prediction minus the highest label that is not highest prediction that is not true label. And path norm, I mean, you can just compute it from the weights. So you can do it at any time t, but I did it at different iterations to see how it changes throughout training. But the point here, I mean, the exact expression doesn't really matter. You can look up Nature et al. Paper on path norm. There are actually a couple of different papers on how to do the calculation more efficiently. But what does matter is just the kind of the way that these quantities grow throughout training and what bounds they induce. And that's really what I wanted to highlight, is that they're obviously they don't have the right ratios to produce bounds that explain generalization by themselves. And one could argue the constants are off and then so on, and there's a whole different discussion there, and I'll get a little bit to it later. But to start with, it's clear that we can't get a non-vacuous bound for a good predictor using these techniques. Okay, so let me return to PAC-Bayes. So in my work, I studied a posterior classifier Q, which was a Gaussian, isotropic Gaussian, centered at the weights found by stochastic gradient descent. So I just run stochastic gradient descent as usual, find some weights, center Gaussian there, and try to have as large of a variance as possible without increasing my empirical risk too much. So in our uriad paper, we exploit flatness via PAC-Bayes by combining it with non-convex bound optimization to obtain first non-vacuous bounds for overparameterized deep neural networks. And unlike contemporaneous work on bounds, we focused on empirical evaluation from the very start. But there are a few weaknesses in that work. So the bounds were still numerically too loose to explain observed generalization. So there we were looking at binary MNIST, for example, and we were getting classifiers with like 3% error and 17% bound on the error, which of course there's a large gap, and it's MNIST charts, so we would expect even the randomized classifier to perform better. Also, these bounds hold only for perturbed classifiers, not the original classifiers, right? So I had to perturb my stochastic gradient solution with a Gaussian to get a bound at all. And the bounds also don't scale correctly. So you can see kind of in my paper already that as we increase, for example, the width of the network, I believe for the depth of the network, the bounds were actually increasing a little bit. And the bounds depend heavily, due to the choice of the Gaussians, it depends heavily on the distance of the weights to initialization. So what are we missing? What are the barriers to explaining generalization? Well, there are 3 barriers that I'll be discussing in this talk. One is statistical barrier, another one is computational barrier, and the 4th barrier is analytical barrier. So by statistical barrier, I mean that generalization may rely on favorable properties of the data distribution, but real-world data distributions are, of course, unknown, right? We only have access to the samples from the data distribution. There are also computational barriers. Generalization may rely on quantities that are known but are hard to compute, such as the distribution that as you desampling from. And by analytical barriers, I mean that generalization may happen in ways that our current mathematical tools cannot capture. So perhaps we just, we need new tools, and maybe uniform convergence is not sufficient, as pointed out by Nagaraj and Coulter. So let me transition to overcoming statistical barriers in PAC-based bounds via data-dependent priors. So note that tight PAC-based bounds depend on the data distribution, which is of course unknown. So consider a data-dependent posterior Q, right? So we fit a posterior Q that is data-dependent, let's say by training stochastic gradient descent on our data S. Then PAC-based theorem binds generalization here in terms of KLQ and between Q and P, this data-dependent Q and P. And it's well known that the prior minimizing the KL term in expectation is a distribution-dependent prior. So a prior P star minimizing KLQP equals to the expected posterior classifier Q. So a prior is a prediction, right? We're trying to predict where Q will end up using the data. And of course, the unknown data distribution is a statistical barrier. So PAC-based has this fundamental tension. PAC-based prior P can depend on the data distribution D, but it cannot depend on the sample. But our only handle on the unknown data distribution D is the sample, is for the sample S. But in fact, one is wrong. So first, a couple of years back, we showed that data-dependent PAC-based, that priors learned in a differentially private way yield valid PAC-based bounds. So for as long as you use the data carefully in a differential private way, you can learn the prior based on the data. Of course, there is an extra penalty term coming from how much privacy you leaked, but still, the prior can depend on the data. And there recently, at our work that we just presented at AStats, we also show that even if you know the data distribution, using some of the data, so having a prior that is distribution and data dependent, might actually outperform just purely a distribution dependent prior P. Now this, there has been quite a bit of work in the past, and I cite here one piece of work, where people try to use data to approximate the distribution dependent prior, but that's not really what I'm talking about. So informally, we show that there is a distribution loss in learning algorithm, so some learning setup such that a PAC-based bound with the oracle prior P star, which is this expected posterior, is vacuous, but the same bound that is distribution and data dependent, so P star that depends on a training subset S prime, and P star equals then this conditional expected posterior, where we condition on the subset of the data that the prior has access to, is non-vacuous. So in other words, what this is saying that this data and distribution dependent prior can outperform purely a distribution dependent prior, which is quite different from previous work. So to kind of understand this better, consider running stochastic gradient descent with decreasing step sizes on this toy optimization problem, and assume that our priors and posteriors are Gaussian. So posterior will have it somewhere here at the convergence of some variance. The prior P, let's say we don't have any access to the training data. And let's say we center it here at initialization. Then the KL divergence between two Gaussians will depend on the L2 distance between the final weights and the initial weights, reweighted, of course, by the variance, but let's say we have isotropic variance for now. If you allow the prior to have access to a few data samples, then you can actually totally mimic the initial training run and then continue running on the small subset of the data that you gave it access to. And we see that the prior converges somewhere much closer to the posterior center. If you allow it to access even more data, you'll go even closer, and even more data, you'll get even closer. Of course, there is a trade-off, because if you recall, let me just go a few slides back, actually. The PAC-based bound depends on the KL divergence, which is now decreasing as we make P data dependent, but we are dividing by the number of samples that Q had access to, but not P. So the more P has access to, the smaller this number that we're dividing by. So there's, of course, a trade-off, how much data you want to use and how much you want to decrease the scale divergence. Okay, let me get back here. So up to this point, we saw that Gaussian perturbations of the stochastic gradient descent learned predictor allowed us to capture the role of flat minima in generalization. So we exploited this invariance to perturbations, insensitivity to perturbations. And next, I'll transition to discussing Gaussian perturbations at every gradient step instead of only at the end. I'll be perturbing the weights every gradient step. And this will allow me to capture the role of mid-batch gradient covariance in generalization. So before I switch over, are there any questions about this part? Okay, I'll move on. So, so here's a standard stochastic gradient descent update, right? We learn the weights at t+1, which are the weights at the previous time step, minus learning grade A to t, reweighing the gradient update of some objective f, such as a loss or maybe a loss of some explicit regularization or whatever else. Here we'll be adding Gaussian noise. So epsilon t is sampled from a Gaussian that is reweighted with this A to t and the learning grade and some scale parameter beta t. Now, for particular choices of eta and beta, this corresponds to stochastic gradient longitudinal dynamics, and that's what I'll be focusing on, though this could be extended really to any other smoothed versions of stochastic gradient descent. So this additional noise term makes SGLD much easier to analyze compared to stochastic gradient descent. And this parameter beta, which is called the inverse temperature parameter, it trades off exploration versus optimization. So looking at this toy example here on the bottom right, imagine that you start your optimization here at the x. If your inverse temperature parameter is really large, you will basically be not perturbing at all, and maybe you'll do something closer to SGD, which would be converging to this next minima here. But if your inverse temperature parameter is small, then you'll be perturbing every gradient step the weights quite a bit, and so you might be doing quite a bit more sampling, and maybe sampling somewhere here, and so on. So there are two views that one can take of SGLD. So one is that it samples from Gibbs distribution with density proportional to exponentiated empirical risk, or your objective rescaled by the inverse temperature parameter. But this only happens really under unrealistic assumptions, so you need to run for a long time and so on. Another view is that it optimizes, but the resulting weights don't carry too much information about the training set S. And this is a view that I'll be focusing on and asking whether this view explains generalization. And I'll do so by using mutual information bias, which let me introduce these right now. So let S, just as before, note training data, which is sampled ID from our unknown data distribution D, and we have n samples. We'll denote by W the learned weights, which are the output of our algorithm running on the training set S, and maybe using some additional randomness U, which could be, random initialization, random mini-batch order, or these Gaussian perturbations that we use at every step. Then the expected generalization error is defined as the expected difference between the risk of a classifier and empirical risk of the classifier, so between essentially test and training errors. We assume that the loss is bounded. Then Jun Roginski and other people before that, they showed that the absolute value of the expected generalization error of the classifier W, which was learned on the training set S, is bounded in terms of the mutual information between W and S, and between the weights and the data set. So does this theorem explain generalization of SGLD or these other versions of smooth versions of SGD? Well, there are two barriers again. One is a statistical barrier. The mutual information term actually depends on the unknown data distribution D. And there's a computational barrier. Even if we knew the data distribution, the mutual information term would actually be intractable because we can't really, we don't have a nice expression of the distribution that SGD is sampling from, or SGLD is sampling from, and at least when you're running it for a short amount of time. So let me start by addressing the computational barrier and really explaining how people addressed it in the past. So the computational barrier, to repeat, is the following. Even if the data distribution were known, the mutual information term is intractable. So let ST denote random mini-batches of our training set S at time t. Then Pensia, Jung, and Low observed that chain rule implies that mutual information between the training set S and your weights at the end of training is bounded in terms of mutual information between S and now the whole trajectory from the beginning to the end of training, which using the chain rule can be bounded by the sum of these stepwise mutual informations. But you're measuring mutual information only between the weights at time t and the mini-batch that you have that you use to get to those weights, conditioned on all the previous trajectory up to that time, so up to t-1. So in words, it says that the information leaked about the data by the final weights is bounded above by the sum over mutual informations or information leaked about mid-batch at any step time t. So the next hurdle, of course, is to overcome the statistical and computational barriers of computing this one-step mutual information, right? So the barriers still remain even if we decompose it stepwise. But actually, the problem is not much easier, as we'll see. So we'll use the following insight, which is that mutual information, this one-step mutual information, is the optimal expected loss in the following prediction game. So let me define the game now. And the game is the following. You get to observe the trajectory up to time t, and you want to estimate the posterior classifier Q on the weights, which depends on the whole trajectory up to time t, which is observed, and the mini-batch at time t. So it's a distribution on the weights at time t+1, given everything, all the information prior to that, and the mini-batch. Now, of course, you did not get to observe ST. ST is an unknown information to you. So your prediction is some prior on the weights P that can only depend on the trajectory up to time t. And in this game, you'll be paying a loss, which is the Kehl divergence between QP. Then the optimal strategy, just like it was in PAC-Bayes theory, actually, is P star, which is the expected posterior given the trajectory. And its expected loss is actually the now expected Kehl divergence, which turns out to be exactly equal to this one-step mutual information. So here's the key idea. Every prediction scheme P, so any strategy P you take, yields an upper bound on the mutual information because P star, which gives you the mutual information, is optimal. So for all P, the expected loss that you'll be paying for the strategy P will be an upper bound on the mutual information. Now recall that, so we're studying SGLD, which has a Gaussian noise at every step, which makes Q to take a simple form of the Gaussian. So now Q equals the Gaussian, which is now centered at the weights after the update, which depend on ST, and with variance that depends on this variance of the additional noise term, right? Because if you know the location, you got the minimatch, you know exactly where you'll go, and now you're just perturbing it with a Gaussian, right? So Pense, Jug, and Low kind of, took kind of used exactly these insights, though they didn't really present it as a prediction game, but let me present it from this prediction perspective what they did. So they bounded the mutual information in terms of the stepwise mutual information using chain rule, just as I showed you a few steps back. And they play the following game. So the game is the same. You get observed trajectory up to time t. And the goal is to estimate this posterior Q, which for on the next weights, which is a Gaussian centered at the current weights at WT plus 1 with the known variance term. And what Pense, Jug, and Low choose as a prediction is this P, which is also Gaussian, but it's centered at your current location because you don't have the data, so you don't know where it will go next. So they just center it at the current location and use the same variance term. Now they'll be paying a loss, which is scale divergence between Q and P. Since the variances are the same as the Gaussians, this of course will just end up being the difference between the means, which is the size of the gradient. And they bound it above by using Lipschitz constants. So the final bound looks like this kind of stepwise sum of learning rate, inverse temperature parameter, and Lipschitz constants. And of course, when it comes to bounds, first of all, there are a few issues right away, right? This will always be growing, and Lipschitz constants can be very large. So the limitation of this mutual information bound is that it must predict the next set of weights given the previous trajectory, but it has access to no data at all. And so they had to make this worst case estimate. And the way that we propose to solve this is by using conditional mutual information, where we condition on all but one data point. So here's how the game changes when you allow yourself to condition on all but one data point. Now you get to observe not only the trajectory up to time t, but also all the data except for the jth data point. The goal is still to estimate exactly the same Q as before, exactly the same Gaussian that depends on all the training data minibatch ST that may or may not contain the jth data point. And now we can make the following prediction P, which is a lot more informed. So if the minibatch ST, if we have all the data, if S not J contains all the data that appeared in the minibatch ST, so if ST is a subset of the data that we have access to, then of course we can just predict Q. We're all good, right? We have all the information we need. And otherwise, if the data point that we're missing appears in the minibatch, then we'll be making a prediction, which is a Gaussian. But now its center depends on this gradient step, where we only compute the gradient on the data that we did have access to. So in the minibatch, excluding the jth data point. Then we'll pay a loss if we predict a Q. Of course, the loss will be 0 because KLQP for Q close P, it's just 0. And in the second case, we will have the KL divergence will depend on this difference between the full gradient on all the minibatch data versus the gradient on the data that we had access to. And we refer to this term as a gradient incoherence term, since it's measuring how different my gradients became once I excluded this data point. And now we can combine with exactly, same like stepwise decompositions of the mutual information, just replace the last step by bounding the stepwise mutual information with this bound to get a bound on generalization error. So we compared the bounds in practice for networks trained on MNIST, fashion MNIST, and CFAR data sets. So let me just walk you through the plot. So on the x-axis is the training epochs. On the y-axis is the size of either our incoherence term, which is the red curve, or the gradient, the size of the gradient, which is the blue curve that appears in those other bounds. So there are a couple of things to note here. For MNIST and fashion MNIST, the gradient norms, they never vanish. So the blue lines, they kind of remain flat. But the incoherence term do decrease, right? Especially here, we see that the values, I mean, and here as well, the values become very, very small. So it's actually vanishing, which is great, right? Because if you recall, our bound depended on the sum of these, the size of these terms, summed over training time. However, for CFAR, we see that this incoherence term does not diminish, right? So we're obviously missing something that I'll talk about in just a couple of slides. Also, here, the bounds itself. So we computed the bounds. We evaluated some other bounds that appear in the literature, which are the top two curves for different learning rates and inverse temperature parameters. And here are kind of the same parameter settings for our bound. And we see that just within a few epochs, modal bounds, which are competitive with ours, are exploding and becoming vacuous, whereas ours slow down in the way they grow and kind of remain on vacuous for much longer. But of course, the values are still very large, so there's a lot of improvement to be made. So let me now address this issue of the bounds growing or non-diminishing for training time. So the limitation of so what I just presented appeared in our NeurIPS 2019 paper. And the limitation of our work then was that there was no control over the missing data point. So here's how we solve it in our NeurIPS 2020 paper. Assume that the training set S is either equal to S prime or S double prime, where S prime and S double prime differ by only a single data point. And we'll be conditioning on the union of S prime and S double prime, which we'll refer to as a supersample. And these ideas built on the ideas presented in Steinke and Zekin's new paper on conditional mutual information, where they built larger supersamples and do a lot of cool things with them. So now the prediction game looks like this. We get to observe not only the trajectory up to time t, but we also get to observe this supersample, one of which, S prime or S double prime, is the actual training set. We want to estimate still the same distribution Q. Note that in this work, I'll be analyzing full batch longevity dynamics. So I'll have no mini batches anymore. S will be the full size training set. Then the prediction we make is the following. So P will be equal to one of the two Gaussians. So the probability theta, it will be equal to a Gaussian, which is centered based on the gradient computed on this potential training set S prime. And another Gaussian will be centered based on the gradient computed on the set S double prime, right? And we don't know which of this is our training set. So we'll assign probabilities to these. Now, note that the past iterates, so the trajectory up to time t, provides evidence on which of S prime or S double prime is our actual training set. So formally, we have a binary hypothesis test, and this weight theta is chosen based on conditional distribution of missing data points identity. So for example, if at initialization, we have no information and we cannot tell which of these two samples in our supersample is in the training set, S prime or S double prime, we'll assign equal probability to them. Theta will just be equal to half. But as we continue to train, we'll be getting information from the trajectory, which of these two is the actual training set, and we'll be able to do much better, decreasing our KL divergence. So we again evaluated these bounds empirically. Here are the results on MNIST on the left-hand side. The red curve is a competitive bound by Lee et al. From 2020. The green line is our NeurIPS 2019 bound, which did not take advantage of the trajectory up to time t. And the blue line is our new CMI bound that learns from past trajectory. And we see that, in the beginning of training, it might be paying a larger penalty for not knowing which are the training points which are the points belongs to our training set. But after a lot of training, our new bound gets better. And this actually, on MNIST, there isn't that much of a difference. But in CFAR, we see a huge difference. Our bound from previous year, it's really exploding here. But this CMI bound, which takes advantage, learns from past iterations, it pays, again, a large penalty initially, but it plateaus and it stops growing for training time, which is kind of the quality we were looking for. So far we've seen that we can exploit flatness by adding noise to the final weight. So that was the PAC-Bayesian analysis. We can exploit gradient coherence by perturbing iterates with noise. This was the SGLD analysis that I just described. And we can use data-dependent price to reduce impact of initial and stable optimization and of not knowing the data distribution D. And we use conditional mutual information to reduce the impact of measuring information leaked by the entire optimization trajectory. But there is an important caveat. So far we bounded generalization error of perturbations of stochastic gradient descent, which is of course not the same as bounding generalization of SGD itself, of the weights learned by stochastic gradient descent. So how can we bridge this gap? Again, before I transition to the next bit of the talk, I just wanted to double check if anyone has questions from the from the information-theoretic analysis or anything else. So far we bounded generalization of SGD through these kind of so-called surrogates, right? So let W hat be the weights learned by stochastic gradient descent, and let V tilde be some kind of perturbed weight distribution. So for example, we may be perturbed at the end, during every training step, or whatever else, right? And we'll refer to V tilde as a surrogate classifier. So what we've done so far is we bounded the risk of this surrogate classifier by its empirical risk plus some generalization error of V tilde. And the bounds that we had are, can be seen as uniform convergence bounds. And so we're actually upper bounding the risk using the empirical risk of W tilde plus the worst case generalization error of any classifiers belonging to some kind of surrogate class P, for example.
Hi. So
yeah,
there are a couple questions. Sorry. First is, how expensive was it to compute the previous bounds? Like we had examples in Flash MNIST and CFAR, but like if you wanted to use that for ImageNet, would it be too expensive? Or
so there are a couple of complications. So on ImageNet, the CMI bounds would not work directly because at least the bounds that we put there are for full batch. And but people, I believe, have extended that work for mini-batch versions. And otherwise, I mean, it is expensive for sure. You can scale it up on ImageNet, but it's not just like the same as just training once.
Got it. And all of the results in this talk will be about classification, right?
Yes, all about classification.
Got it. Thanks.
Well, I mean, it's about bounded loss functions at least, or you can extend it to sub-Gaussian, but things in some cases get more complicated. Mutual information bounds do extend though, and PAC-Bayesian bounds extend. Okay, so yeah, what we did so far was can be seen as a surrogate classifier analysis, where we bounded generalization error in terms of worst case generalization error of the surrogate belonging to some surrogate class. Now, the direct approach via uniform convergence would look like the following. So we would be bounding the risk of W hat, the actual classifier obtained by SGD, by its empirical risk, plus again, worst case generalization error of W belonging to some class of classifiers, right, that we're optimizing over. Now, the indirect surrogate approach can be connected to the original classifier. So the risk of W hat can be bounded in terms of empirical risk of the surrogate plus the generalization error of the surrogate, the bound on the generalization error of the surrogate, plus the difference between the risks between the original classifier and the surrogate. So far, we've focused really on kind of this part, but there is, if you want to obtain bounds on W hat, you also have this additional term to analyze, which is risk difference between surrogate and your original classifier. So is it worth the trouble going for all this, indirect analysis for surrogates instead of directly analyzing W hat? Well, so far empirically, no direct approach gives numerically non-vacuous bounds. And a potential reason for this could be the analytical barrier of uniform convergence bounds pointed out by Nagarajan and Coulter in 2019. So they observed that in norm-based bounds, the norm terms grow faster than square root of the number of data points you have, hence implying that norm-based bounds scale incorrectly with the number of data. They also in their work gave a toy example where HUD learns a good classifier with small risk. Nonetheless, their generalization error, the uniform bound on the generalization error is it does not give you small risk. So it doesn't, showing that the classifier does not belong to a class with uniformly small generalization error. Hence implying that standard uniform convergence arguments may fail to explain deep learning, at least when used directly. So does this, do these observations pointed out by Nagarajan and Coulter undermine the indirect surrogate approach? Well, not necessarily. Oops. So for any surrogate hypothesis W hat, I'm just repeating the decomposition I had earlier, really in a different form. The generalization error of W hat can be, of course, expressed exactly as the risk difference between your surrogate and original classifier, the empirical risk difference, which is this last term between W hat and W hat and V tilde, and the generalization error of your surrogate. So the generalization error of your D can be broken down into these three parts, right? The error from the approximation by the surrogate, the generalization error of the surrogate, and we can bind this uniformly over a surrogate class, just as we did before. And our approach relates the generalization error of HUD to the generalization error of a better behaved surrogate classifier, which makes the the surrogate classifier might belong to actually a class that has uniform convergence, making the analysis much easier potentially. So the toy example of Nagarajan and Coulter admits a surrogate analysis by uniform convergence. We show that the bias, by using the surrogate decomposition, we show that bias variance analysis of overparameterized linear regression presented in by Bartlett, Long, Vogosian, Ziegler is a surrogate decomposition can be uniform. So this is work that we presented at ICML last year. And we show that surrogates can be defined by probabilistic conditioning in order to ensure risk difference is zero in expectation. So if you actually construct surrogates by conditioning by conditioning on some of the information that W hat depends on, you get rid of this first term, the risk difference, and you're only left with the generalization error of W hat and W tilde and the empirical risk difference between your surrogate and original classifier. I won't go into details right now, but this is the work that's presented in our ICML paper. It kind of defends uniform convergence and shows how to use uniform convergence indirectly. So let me go back to connecting surrogates to HUD. So far, we've discussed generalization bands for two classes of surrogates. Gaussian perturbations are the weights obtained at the end of training by stochastic gradient descent, and Gaussian perturbations are the weight at every step t. Can we control the risk difference term to get a surrogate decomposition? Well, empirical observation is that all proposals to so-called de-randomized PAC-based bounds, so connect the risk between surrogate and original classifier, produce vacuous bounds. And the explanation could be that the arguments that people provided so far are too uniform, which would contradict Nagarajan and Coulter approach. And this is really the part that I haven't really addressed in my work, which is connecting this the risk of the surrogate to the original classifier. But it's obviously one of the key parts for proving generalization of your original classifiers. And my work so far focused, and that I want to address further, is the following question: what structure or empirical phenomena might surrogates exploit? And looking forwards, I would like to exploit optimization and training dynamics and the various phenomena that have been presented in the literature, such as like linear mode connectivity and decay dynamics and so on. So actually, I won't go into over these slides right now. Let me just skip these and go to the conclusion. So to conclude, good generalization is a product of favorable properties of the data, algorithm, and of course the interaction between the two. So the bounds have to depend on the training samples to be explanatory of at least generalization and deep learning and standard settings that we see. And they also had to depend on the data distribution. Of course, now if you have data distribution dependence, empirical evaluation is needed. So it's empirical evaluation of generalization methods and measures is critical. Complexity terms are data dependent, and empirical evaluation is the only way to know how they grow, where the bounds may fail, and where we need to improve to make progress. And we talk a little bit more about this in our last year's NeurIPS paper, named In Search of Robust Measures of Generalization, I believe. Also, capturing data distribution dependence by using training samples allows us to circumvent statistical and computational barriers when evaluating theories. And we've seen some of that already in my work on using data-dependent priors in PAC-Bayes, or again using data dependence to improve information-theoretic bounds on HLD. Instead of bounding the generalization uniformly over a hypothesis class containing the predictor, we should think about related predictors, so-called surrogates, that may belong to a class where uniform convergence does hold, right? So again, while uniform convergence approaches may fail when you're studying the class of predictors that the classifier you're interested in belongs to, there may be some related classifier that belongs to a nicer class, right? And doesn't contradict necessarily the observations pointed out by Nagaraj and Coulter. And we have made progress in studying some surrogates, so by perturbing the classifier stepwise or at the end, as I showed, but there's, of course, still a lot of work to be done. So there are both of these parts that still had to be solved, which is relating risk of the surrogate to original classifier, but also just understanding what surrogates lead to good generalization, what surrogates we should be studying. Okay, that's it. Thank you very much.
Okay, thank you very much for the talk. Let's wait a little bit, see if any other questions appear. And yeah, I guess my main questions are those relating to how easy it is to compute that kind of stuff. Because I think right now we don't have good diagnostics of neural networks.
Yeah. So how easy it is to compute? So with PAC-Bayes bounds, for example, it does require additional optimization steps. So you do need to optimize at the end of training to make PAC-Bayes bound in order to find good variances and so on, to diminish scale divergences and so on. But of course, don't forget that you'll get a bound on this perturbed classifier, right? So you'll get a bound on a classifier, which first samples a set of weights, then makes a prediction, right? Mm-hmm. Which is, of course, not the same. Of course, you could also, some interesting approaches that we presented in one of our papers, in the A-Stats paper on the role of data in PAC-Bayes bounds, are to optimize the bounds directly from the very beginning. So perhaps you can start by learning the bound some of the data and then continue the optimization on all of the data to optimize posterior while minimizing the bound, which is, of course, again, not the same at all as explaining generalization of stochastic gradient descent, but it might be interesting if you're just looking to obtain a classifier with guarantees, for example.
And do you know if that kind of thing has been implemented in code, in libraries, because again, I think like right now we sometimes have papers showing how we get bounds, how we understand how much our networks are really learning, are really generalizing. But then when you see like the day-to-day practice, people just like pick the accuracy and go on with that.
Yeah, so I don't think they're in any libraries. I mean, I did release my code for doing these computations. However, I will say that, I mean, they're so far this point from holdout bound, and I'm not sure they'll get there, to be honest, because the purpose is more about understanding it's different. That, you know, no one in practice would want to necessarily compute a generalization guarantee if they don't have a crazy amount of data, and instead they'll do held set bound. So I think, you know, only kind of in scenarios where you have crazy amounts of data, you might be interested in trading off performance for getting a guarantee, because there's always this trade-off. But in standard settings, you're much better off by looking at a held out set bound, because you'll get a better performing predictor.
Got it. And there's a question for the chat. It's, can you please suggest some direction, I think some like resources for out of distribution generalization? So I guess we're concerning that.
For out of, yeah, so I haven't worked myself actually on out of distribution generalization so much yet, but I'm very interested in it, and have some work being started. There are, I mean, there are so many papers on the topic that I feel like I don't have a good enough grasp to suggest anything concrete yet, though that person is welcome to reach out to me in private, and I'll recommend some papers that I looked at. And there are lots of interesting papers by Sham Kakadi or Jason Lee on studying, for example, linear classifiers to start with. And I believe in general, the foundations still need to be built there. So there's a lot of interesting work to be done. But yeah, I can't really recommend at this point like concrete papers, because I haven't worked on it enough to know the field.
Yeah, makes sense. So thank you very much for the presentation, and for everyone watching, Karolina will be back in our closing panel. So thank you very much,
Yes,
and
yeah.
bye.
Thank you.